Hardware design today is still a slow manual process. Writing RTL, fixing syntax errors, compiling designs, and verifying correctness can take hours, even for relatively small modules. While AI has transformed software development workflows, hardware design is still missing an end-to-end and intelligent verifiable pipeline. This is the problem we aim to solve.
My name is Ben, and this is Ruben. Together, we aim to solve this problem.
SiliconForge is an autonomous agent-based RTL design and verification system. It takes a natural language hardware specification, converts it to a synthesizable SystemVerilog, compiles it using a real RTL toolchain, and validates the result automatically. Instead of treating hardware generation as a one-shot task, SiliconForge treats it as a closed-loop engineering workflow. The goal is not to generate RTL, but to generate correct simulation clean hardware designs.
This diagram shows the end-to-end architecture of SiliconForge. On the left, the user interacts through a React-based frontend where they enter a natural language hardware specification and view logs, RTL output, waveforms, and FSM diagrams in real time. That prompt is sent to a fast API backend, which acts as an orchestration layer. Here, requests are validated and passed into core EDA agent pipelines. At the heart of the system is an autonomous loop. An architect agent generates synthesizable system Verilog, which is then compiled using Icarus Verilog and verified through simulation. If compilation or simulation fails, structured error feedback is collected and routed back into a self-repair loop, allowing the agent to iteratively fix the design instead of failing silently. Once verification succeeds, real simulation artifacts such as waveforms and reconstructed FSMs are generated and sent back to the frontend for visualization. Throughout the process, SiliconForge integrates real hardware tools and real LLM reasoning, ensuring every design is verified, traceable, and engineeringly correct. Now, let's jump into the demo. What you're seeing here is SiliconForge, an autonomous hardware design system. Instead of manually writing RTL, test benches, and verification logic, we give it a natural language prompt. Here, I have asked SiliconForge to design a SPI controller using SystemVerilog. You'll notice this takes some time to run. That's intentional. SiliconForge is not just generating code, it's actually executing a full hardware verification pipeline. Under the hood, this includes RTL synthesis checks, compilation, simulation, verification, and visualization. So I'll explain what's happening in the backend right now. First, an LLM-based architect agent converts the prompt into synthesizable SystemVerilog RTL. The output is constrained to be compatible with real simulators like Icarus Verilog. This is not pseudocode. This is a real RTL that can be compiled and simulated. Next, SiliconForge compiles the generated RTL using a real Verilog compiler. If compilation fails, a debugger agent analyzes the error and automatically patches the RTL, just like a human engineer would. Once compilation succeeds, the design is structurally analyzed. SiliconForge inspects the AST of the RTL to detect things like whether the design contains a clock, whether it has reset logic, etc. After that, a CocoaDB test bench is generated and executed. This runs an actual event-driven simulation using Python-based test logic, not mock checks. If all tests pass, we do consider the design verified. As part of the simulation, SiliconForge captures real simulation traces. These traces are converted into waveform data and plotted automatically. SiliconForge also parses the RTL to extract finite state machines. It identifies state enums, next state logics, and transitions, and then generates a structured FSM diagram. This diagram reflects the actual RTL behavior. It's not AI-generated art. Each state and transition corresponds to logic in synthesized design. The key idea here is that SiliconForge doesn't just generate code, it closes the loop. It generates RTL, compiles it, fixes errors, verifies behavior, and produces engineering artifacts like waveforms and FSMs. This is the workflow real hardware teams follow, but here it's fully autonomous. In real engineering environment, this pipeline could save days of iteration per module. For this demo, we are showing a single design, but the same system can scale to much larger blocks. SiliconForge is essentially an autonomous hardware engineer, not just a code generator.